Welcome to today's episode, where we're diving into the fascinating and often complex world of data propagation in distributed systems. As technology advances, grasping how data is shared across multiple nodes becomes more important than ever. We'll explore why efficiently sharing cluster-wide metadata matters, the challenges that arise from different communication methods, and the innovative solutions that help us maintain data integrity and consistency. At the core of distributed systems is the challenge of data propagation. This is all about the timely and reliable sharing of metadata, which includes crucial information like node states and membership details across a cluster. As systems scale up, the complexity of keeping this information accurate and up-to-date grows significantly. To illustrate this, let's look at three primary communication approaches: broadcasting, peer-to-peer exchanges, and cooperative broadcasts. Broadcasting is a simple method where a single message is sent out to all nodes, making it a good fit for smaller clusters. However, as the number of nodes increases, this method can become inefficient and may lead to unreliable message delivery. When that happens, we're left with outdated or inconsistent data across nodes, which is a major hurdle for the functionality of distributed systems. To tackle the limitations of broadcasting, we can turn to peer-to-peer exchanges. This approach allows nodes to communicate directly with each other, cutting down on the overhead that comes with broadcasting messages to the entire cluster. While this method boosts efficiency, it also adds a layer of complexity as we need to manage direct connections and ensure that all nodes stay in sync. Then we have cooperative broadcasts, which strike a balance between the two. In this model, nodes collaborate to spread information, enhancing reliability and reducing the chances of message loss. Each method has its own set of pros and cons, and the choice of which to use often hinges on the specific needs of the system and its scale. Now let's discuss one of the significant challenges in distributed systems: ensuring that messages are delivered reliably, even when failures occur. This is where the concept of anti-entropy comes into play. Anti-entropy is a synchronization mechanism that helps nodes reconcile their states, ensuring consistency even when some updates miss their targets. Within this framework, we have two effective strategies for maintaining data integrity: read repair and hinted handoff. Read repair comes into play during read operations. It detects inconsistencies and triggers updates to ensure that all nodes reflect the same data. On the flip side, hinted handoff allows updates to be temporarily stored for nodes that were offline during a write operation. This means that no data is lost, as the updates can be delivered as soon as the node comes back online. As we dig deeper into maintaining consistency, we come across Merkle trees, a powerful tool for efficiently identifying discrepancies in replicated data. Think of a Merkle tree as a hierarchical organization of data, where each level is made up of hashed values that culminate in a single root hash. By comparing these root hashes between replicas, we can quickly spot discrepancies and target specific data ranges for correction. The process of recalculating hashes is recursive, meaning that any change in data necessitates recalibrating the entire subtree. This creates a balance between the size of the tree and the precision of the data representation. Merkle trees significantly streamline the data reconciliation process, allowing for quick identification of inconsistencies without the need to compare entire datasets. In addition to Merkle trees, we've seen advancements like bitmap version vectors, which enhance conflict resolution in distributed systems. These vectors keep a log of operations at each node, enabling them to compare logs during data synchronization. This method ensures that missing information is effectively replicated, as each write operation is tracked with a unique sequence number. By maintaining a clear record of changes made by each node, bitmap version vectors facilitate more efficient conflict resolution. When discrepancies arise, nodes can consult their logs to determine the correct state of the data, allowing for targeted updates and minimizing the risk of data loss. The combination of anti-entropy, read repair, hinted handoff, Merkle trees, and bitmap version vectors plays a crucial role in maintaining data consistency across distributed systems. Together, these mechanisms ensure that even when faced with challenges like node failures or network partitions, the integrity of the data remains intact. As distributed systems continue to evolve, the significance of these strategies cannot be overstated. They lay the groundwork for building reliable and resilient systems capable of navigating the complexities of modern data management. As we wrap up today's exploration of data propagation in distributed systems, we've highlighted the importance of efficiently sharing metadata and maintaining data integrity. We've touched on various communication approaches, the challenges posed by message delivery failures, and the innovative solutions that have emerged to tackle these issues. By leveraging mechanisms like anti-entropy, read repair, hinted handoff, Merkle trees, and bitmap version vectors, distributed systems can enhance their reliability and consistency even when the going gets tough. As we continue to navigate the intricacies of data management in our increasingly interconnected world, understanding these concepts will be essential for anyone involved in developing and maintaining distributed systems. Thank you for joining us in this episode. We hope you found our discussion insightful and that it enriches your understanding of the complexities involved in data propagation within distributed systems. Stay tuned for our next episode, where we'll explore more exciting topics in the realm of technology and data management.